In this experiment, we will titrate a weak acid with a strong base. The objective of this experiment is to determine the pKa value in molar mass of an unknown weak acid by titrating with standardized sodium hydroxide. The sodium hydroxide will be standardized using the primary standard potassium hydrogen phthalate, or KHP. The pH plot will be made using data from a pH meter and probe. Before we begin, we need a few definitions. When we talk about the formal concentration of a solution, this is the concentration that is written on the bottle. In many cases, the actual concentration of a species in solution is equal to the formal concentration, but not always. If you were to make a 0.500 molar solution of sucrose, table sugar, in water, then we know that we have 0.500 moles of sucrose per liter of water. This is a case where the actual concentration equals the formal concentration. However, if you make a 0.500 molar solution of sodium chloride, table salt, in water, we don't have any sodium chloride actually in solution. We know that all of the sodium chloride dissociates into sodium ions and chloride ions. The concentration of each of these ions is now equal to the formal concentration of the solution. Now for some definitions of acids and bases. Under the Bronsted-Lowry definition, an acid is any compound that donates a proton to another compound. A Bronsted-Lowry base is any compound that accepts a proton from another compound. The relative strength of an acid is determined by how readily it donates its proton. Any strong acid will completely donate its proton to a base. As an example, consider nitric acid in water. The reaction is HNO3 plus water, forming hydronium ion, H3O+, and nitrate ion. Because nitric acid is a strong acid, we expect the acid to be completely dissociated. The actual concentration of nitric acid in solution is 0. The concentrations of hydronium ion and nitrate ion are equal to the formal concentration of the acid. Most acids do not behave as strong acids in water. They are considered to be weak acids. A weak acid will not completely dissociate in water solution. For example, acetic acid, CH3COOH, is a weak acid in water. The reaction is acetic acid plus water, in equilibrium forming the hydronium ion plus the acetate ion. Because this is an equilibrium reaction, we know we can write an equilibrium constant expression. In this case, Ka has the concentration of hydronium ion times the concentration of acetate ion in the numerator, and the concentration of the undissociated acetic acid in the denominator. This is a special type of equilibrium expression called an acid dissociation equilibrium constant, and so it's given a special symbol, Ka. The value of Ka for acetic acid is 1.7 times 10 to the negative 4 at 25 degrees Celsius. Recall that since this value is less than 1, we expect the equilibrium to lie toward reactants, and most of the acetic acid will remain in the protonated form, with only a small fraction dissociating to form hydronium ion and acetate ions. The smaller the value of Ka, the weaker the acid is in water. When we relate the relative strengths of acid or base solutions, this is most commonly done using the pH of the solution. In chemistry, whenever we see the lowercase letter p at the beginning of a variable, it always means take the base 10 logarithm of whatever follows it. Therefore, the pH of a solution is defined to be approximately equal to the negative base 10 logarithm of the hydronium ion concentration. Any solution with a pH below 7 is considered to be acidic. Any solution with a pH above 7 is considered to be basic or alkaline. Whenever we mix an acid solution and a base solution, a reaction known as neutralization occurs. When a strong base is added to a weak acid solution, the neutralization reaction is between the weak acid and the hydroxide ion from the strong base. Returning to acetic acid, the neutralization reaction is acetic acid plus hydroxide ion, forming acetate ion and water. At any point during the titration or the neutralization, the pH of the final solution will depend on the volume and the concentration of both the acid and the base solution. A weak acid titration is when we quantitatively react a weak acid with a strong base of precisely known concentration. We add very accurate volumes or aliquots of the base, and these are added sequentially. After each addition, the pH of the solution is measured and recorded. By plotting the pH of the solution on the y-axis and the volume of the base added on the x-axis, we can build what is called a titration curve. Since we are starting with a weak acid, the pH will initially be below 7, and it will increase as we add more base to the solution. The most important point on any titration curve is called the equivalence point. The equivalence point of a titration is the volume of base required to exactly react with all of the weak acid in solution. As an example, let's consider the titration of 0.185 grams of an unknown weak acid with a 0.112 molar solution of sodium hydroxide. Because we are titrating a weak acid, the pH prior to adding any of the base is below 7. As can be seen by the blue dot on this plot, this acid has a pH of about 3.5 initially. In the early stages of the titration, we have added several small volumes of sodium hydroxide. Notice that we still have an excess of acid after each addition. The pH is increasing because we have reacted off some of the acid, but it is still less than 7. In a titration, there will be a region in which the pH changes very little. This is what is known as the buffer region. In this region, there are roughly equal amounts of both the weak acid and its conjugate base in solution. When we add the sodium hydroxide, the pH does not change very much because of the fact that we have a relatively large amount of each of the two conjugates. This is an example of Le Chatelier's principle at work. As we begin to approach the equivalence point, we notice that the pH of the solution begins to rapidly increase. We have to decrease the volume of the titrant being added considerably in order to avoid jumping over the equivalence point. The equivalence point will occur at the midpoint of this steep region. It is important to note that at the equivalence point, the only species that's present is the conjugate base of the weak acid. We have reacted off all of the weak acid and all of the hydroxide ion at the equivalence point. Since only the conjugate base remains, the equivalence point pH for a weak acid will always be higher than 7. After the equivalence point, we have excess hydroxide ion in solution, and this is what now determines the pH. The pH will continue to rise until it begins to level off due to saturation of the hydroxide ion. If we read down directly from the equivalence point to the x-axis, we find that the equivalence point volume for this titration is approximately 14.2 milliliters of sodium hydroxide. We are able to use this value to calculate the moles of acid that we titrated, as well as the molar mass of the weak acid. We are now able to calculate the molar mass of our weak acid. The first step is to begin by calculating the moles of sodium hydroxide that were used to reach the equivalence point. To do this, we take the equivalence point volume, 14.2 milliliters, and convert it to liters, 0.0142 liters. We then multiply this by the concentration of the base that we titrated with, 0.112 moles of sodium hydroxide per liter. The resulting moles of sodium hydroxide are found to be 1.59 times 10 to the negative 3. Next, in this example, as well as in the experiment, we are titrating a monoprotic acid. This means that 1 mole of sodium hydroxide reacts with 1 mole of acid. We can now calculate the moles of acid titrated. We take the moles of base, 1.59 times 10 to the negative 3, and multiply it by our conversion factor of 1 mole of acid per mole of sodium hydroxide. This results in 1.59 times 10 to the negative 3 moles of weak acid being present. The last step is to calculate the molar mass of the acid. We know the mass of the acid we titrated is 0.185 grams, and we know the equivalent number of moles. To find the molar mass, we divide the mass by the number of moles, or 0.185 grams of weak acid divided by 1.59 times 10 to the negative 3 moles of acid. The resulting molar mass is found to be 116 grams per mole. Determining the molar mass of the weak acid is a very good starting point, but there is one additional piece of information that we can gather from the titration plot. This is the value of pKa for the weak acid. Recalling that the lowercase p means to take the negative log of whatever follows it. By definition, pKa is the negative log of Ka. With a little bit of algebra, we can see how to evaluate pKa from the titration plot. We will begin by looking at the acid dissociation expression. Since we do not know the identity of our weak acid, let's denote it as HA. The corresponding acid dissociation equilibrium is now HA reacting with water to form in equilibrium hydronium ion and A-. The acid dissociation expression has the concentration of hydronium ion times the concentration of A- in the numerator, and the concentration of the undissociated HA in the denominator. First, let's take the negative log of both sides of this expression. Notice that I have rewritten the right-hand side slightly differently. This will become obvious in a minute why I did this. The left-hand side of this equation is nothing more than pKa at this point. We can simplify by using the product rule for logarithms. Anytime we take the log of a product, we can rewrite that as the sum of two individual logs. Now we can distribute the negative sign, giving us negative log of the hydronium ion minus the log of the ratio of A- concentration to HA concentration. Identifying the first term on the right as the pH now gives us the equation pKa equals pH minus the log of the concentration ratios. The last step is to move the log term over to the opposite side. This yields the expression pH is equal to pKa plus the log of the ratio of A- concentration to HA concentration. This equation is known as the Henderson-Hasselbalch equation. Now at the equivalence point volume, or VEQ, we have added enough base to completely react all of the HA to form A-. Consequently, this means that when we have reached exactly 1/2 of the equivalence point volume, or 1/2 VEQ, we have reacted exactly half of the HA to form A-. This tells us that when we reach 1/2 VEQ, the concentration of HA in solution is exactly equal to the concentration of A- in solution. This means that the ratio of the concentrations is equal to 1. We can substitute this into the Henderson-Hasselbalch equation, which now becomes pH equal to pKa plus the log of 1. But since the log of 1 is 0, we now see that at 1/2 VEQ, the pKa is equal to the pH of the solution. Let's return to our titration curve. Recall that the equivalence point volume was found to be 14.2 milliliters. This means that 1/2 VEQ is 7.1 milliliters. If we read up to the pH curve and then read back to the pH axis, we find that at that volume, the pH of the solution is about 5.2. This means that the pKa value for this acid is approximately 5.2. Now let's take a look at the actual experiment. This image shows a standard setup for a burette titration. Notice that the burette is being held in place by the burette clamp. We will pour the standardized sodium hydroxide solution into the burette for titrating. The beaker will hold our weak acid solution. It is sitting on top of a magnetic stir plate. The magnetic stir bar will spin, thus stirring the solution throughout the titration. On the left-hand side, you see the pH meter. The arm of the pH meter is extended over the solution and is holding the pH electrode in the solution. Here is a close-up image of the pH meter. Notice that it reads the pH value, in this case 7.54, as well as the temperature of the solution at the bottom. Before we can begin our titration, we must first standardize our sodium hydroxide. The act of standardization means that we determine accurately the concentration of the sodium hydroxide. To perform the standardization, we titrate a primary standard with the sodium hydroxide. A primary standard is a compound that precisely reacts with the base in a known one-to-one stoichiometry. For this, we will use potassium hydrogen phthalate, or KHP. To do this, we weigh out 3 masses of KHP and titrate each to a phenolphthalein endpoint. We can then use the mass of KHP and the molecular weight of KHP to calculate the number of moles, and therefore the number of moles of sodium hydroxide reacted. We can then use the volume required to reach the endpoint and the number of moles of sodium hydroxide to calculate the concentration. The tables show the data from the standardization titrations. The middle column indicates the mass of KHP that was titrated in each run. The third column indicates the volume of sodium hydroxide required to reach the endpoint. For each run, we can use the molar mass of KHP, 204.22 grams per mole, to calculate the concentration of sodium hydroxide. We will then average the concentration for all 3 runs. This calculation will be shown in detail in the next video, but the concentration for the sodium hydroxide in this experiment was found to be 0.0935 molar. Now we can begin looking at our weak acid titration. We need to weigh out approximately 0.2 grams of the unknown weak acid. The actual mass was determined to be 0.238 grams. This was transferred to a 100 milliliter beaker and dissolved in 50 milliliters of distilled water. At this point, we filled the burette with the 0.0935 molar standardized sodium hydroxide, and we begin to add this 1 milliliter at a time and record the pH after each addition. As we approach the equivalence point, the pH will begin to increase rapidly, and so we have to decrease the volume of base added. Around the equivalence point, we will be adding no more than 0.05 milliliters of base each addition. Once we are beyond the equivalence point region, we can return to larger additions, and we will continue to titrate until the pH levels off. Rather than have you watch a video of me perform the titration, which will take approximately 20 to 25 minutes, we will actually form the plot with the data as they're collected. Notice, when we begin with 0 milliliters of sodium hydroxide added, the pH of the solution is 2.53. As we begin to add 1 milliliter aliquots of the sodium hydroxide, the pH begins to increase. After about 10 milliliters, we see that we're entering the buffer region. This is the region where the pH does not change very much, even though we're adding relatively large additions of sodium hydroxide. After we've added approximately 26 milliliters of base, we begin to see a more rapid increase in the pH. We have to decrease the volume of sodium hydroxide that we add for each addition at this point. As we move through the equivalence point region, pH shoots up, and after about 30 milliliters begins to level off again. At this point, we can increase our aliquot volume. Once we reach approximately 40 milliliters of base added, we have plateaued and we can end the titration. Notice from our data that our equivalence point volume is approximately 28 milliliters. The pH of the solution at this point is about 8, which is indeed higher than 7, as would be expected. This concludes the data collection for this experiment. The data for the weak acid titration will be posted in a file on Canvas. In the next video, we will discuss all of the calculations in detail.